Hi, welcome to another 4AC word example tutorial. This time we'll look at a past year exam paper, February 2014, question 3, part A. The question reads, for the circuit in figure 3.1, IR1, the current flowing through this branch of the circuit, is given as 0.7071 sine of 628.32 T ampere. And the other three branches are shown as follows. Now what's required of this part of the question is that we have to calculate the inductance XL and capacitance XC, right? That means we want to know what is the capacitive value of this capacitor and the inductive value or inductance value of this inductor. Next, we want to calculate the total impedance. That means if we look at this as a total load, I want to calculate what is the total impedance. Then we want to sketch and label the impedance diagram. And next, we want to determine the supply voltage ET in phasor form as well as in sinusoidal form. Finally, we want to determine the current flowing through, IS, the total current flowing in here, IC, the current flowing through here, IR2, current flowing through here, and finally IL. All right. All right. Part one. Now, part one, the questions wants us to calculate the inductance value and the capacitance value of these two components, right? So we can start by doing the inductors first, okay? So XL is given as omega L. Therefore, the inductance L is equals to XL over omega. That's equals to 40 ohms divided by omega. Omega is given here, 628.32 radians per second. And that gives me a value of 63.66 millihenry. That's the inductance value here, okay? And for capacitance, Xc is given as 1 over omega C. Therefore, C is 1 over omega Xc. That's equals to 1 upon 30 times 628.32. That's equals to 53.05 microfarad. Please remember to write the units. This is Henry and this is farads. Alright, that's the answer for part 1, part A, sub part 1. Right? Now the next thing we want to do is to calculate the total impedance. Now total impedance is seen from this angle. That means the whole thing here. So they're all in parallel. So I need to use the parallel formula. 1 upon ZT is equals to 1 upon ZR1 plus 1 upon ZC plus 1 upon ZR2 plus 1 upon XL. Okay. Now it is easier to use the complex number of phasor polar version. So I will do everything in polar version. So it's 1 divided by ZR1 is just 100 at the angle of 0 degrees. Here is 0 degrees, okay? Plus 1, 0 degrees upon XC. XC is 30. But because it's a capacitor, it has a minus 90 degrees. And I have 1 upon R2. 1 upon R2 is 100 at the angle of 0 degrees. Plus finally the inductance. Inductance is 40 at the angle of positive 90 degrees. So this 1 upon 100, 0.01 at angle 0, plus 1 upon 30, which is, this is come positive, so it's 0.033 something, okay, plus 0.01 angle 0, and finally minus negative, so I use J, 0.025, 0.40, 0.025, 0.02. That gives me 0.02 in phasor form. Now here is positive, here is negative, so that gives me plus J 0.0083. That is this minus this plus. Okay, that we convert it to the polar form, which gives me 0.02165, the angle of 22.54 degrees Siemens. Therefore, ZT equals to 1 upon 0.02165 and an angle of 22.54 degrees. That gives me 46.189, and an angle of minus 22.54 degrees. Oops. Convert this to rectangular format. There will be 42.66 minus G, 17.71 ohms. Based on what we calculated in part 2, we can then draw the impedance diagram. Impedance diagram basically is to look at these two and say, okay, first part is the resistive portion, which is at 0 degrees, so it's here. So this is 42.6 ohm. Now this is a minus J. Minus J means it goes down this way. It's the J 17.71. And the total impedance is, joining this one up. So this is my ZT with the angle here. And the angle was 22.54 degrees. So that's the impedance diagram. Alright, next we want to calculate the input voltage. So we use the phasor version. Phasor E is equals to, for branch circuit number 1, we have the current IR1 multiplied by the impedance of R1. Now IR1 can be deduced from the sinusoidal waveform. We will have the 0.5 angle 0 degrees multiplied by 100 the angle 0 degrees as well. So that gives us 50 the angle of 0 degrees volt. Expressed in sinusoidal form, be 50 times root 2 sine omega is 628.32 t. It's equals to 70.71 sine 628.32 t. Okay, that's the two answers for the voltage waveform. For the current waveform, if we look at the circuits, I can deduce or calculate my current waveforms by making use of my voltage input. Right? For example, current waveform IS in phasor form. So IS, I can just say IS is equals to E upon the total impedance Z, which we calculated earlier. Right? So that's 50 divided by 0 degree volt over the total impedance that we calculated earlier was 46.189 with the angle of minus 22.54 degrees. Oops. That gives me 1.083 angle 22.54 degrees ampere. Similarly, for IC, I can make use of E divided by ZC. That's 50 angle 0 divided by ZC, which is ZC was 40, which is 30 at an angle of minus 90 degrees ohms. So that gives me about 1.667 at an angle of 90 degrees ampere. Next, IR2 is E over ZR2, which is 50 angle 0 volt divided by R2. The 2 is 100 angle 0 ohms. That's 0.2 angle 0 ampere. And finally, IL is given as E upon ZL, which is 50 angle 0 divided by 40, the positive of 90 degree angle. That's equals to 1.25 at an angle of minus 90 degrees ampere. Alright, so here are all the current in polar form. And that's all for part A.